So let's explore next. First, to have a benchmark, basically the static benchmark, so the case in which there is no stochasticity, so no uncertainty. So the question here is, how would a monopolist choose its K if it would just be one investment? So you have nothing, you will build one plant of capacity K, and you know that demand size theta in this case is just one fixed parameter, so it's not going to evolve just for now. So the question is, so if we want to invest just for once, how much capacity would we invest in? So the cost of making this investment, of course, is going to be I times K. So in this case, what we want to do is, well, we know that when we invest in K, then for the rest of our lives, or in perpetuity actually, we will be able to produce capacity Q equals K. Well, theta is fixed, so demand size is fixed, so it will be the same K every point in time. How much capacity would I want to invest in at this point in time? So in order to figure out how much it is, so we'll have to look at long run profit maximization. So let me do that again. Let me do that on paper. So remember, so our profits every point in time, or profit flow rather is going to be P times Q. Or in other words, it's going to be theta, which for now we've chosen to be constant. This is not moving just for this benchmark investigation. So it's theta times Q to the power 1 minus gamma, and we just saw that actually we're going to choose Q equals K, right? So we're always, it's going to be profit maximizing to produce up to capacity all the time. So actually our profit flow is going to be theta times K to the power 1 minus gamma. So that's what we get each moment in time. So what's our total profits, our long run profits? Long run profits, that's going to be, well, each moment in time we get this amount, a fixed amount. We get this forever, so that's a perpetuity. So that's theta times K to the power 1 minus gamma divided by R. So that's a perpetuity value that we have seen before lots of times already. So we want to maximize our total profits. Well, what are our total profits? Well, the case that we are looking into is, suppose you have no capacity, you want to make once and for all, we want to make investment in these K units of capacity. That's going to deliver to us this particular value, this perpetuity value, but of course there's also cost, and the cost of investing, and that's minus I times K. So I was the per unit investment cost, so I times K is the total investment cost. So what is the amount of capacity K that we would like to buy at this per unit cost I in order to get this perpetuity theta times K to the 1 minus gamma? So in other words, we want to maximize our long run profit, so we want to maximize this thing over K. What choice should we make? So again, what we can do is look at the first order conditions here. So we want to maximize this, so let's look at the derivative. So let's look at ddk of this thing, theta to the power K to the 1 minus gamma over R minus this I times K. What is the derivative? Of course, that's for the first term, that's going to be theta times K to the minus gamma. So taking the derivative with respect to K, so the power here, the exponent goes down by 1, so the 1 is vanishing, and instead we put the 1 minus gamma up front. So that's the first term, derivative of the first term, and the derivative of the second term is the marginal cost of investment. So I again is this investment cost. So what does it mean for K? So it's the optimal K here. Well, that's the one for which the first order condition holds. So this thing should be equal to 0. So what does it amount to? Well, of course, theta times K, let me call this K star, will be this optimum value to the power minus gamma should be equal to R times I divided by 1 minus gamma. So that's the optimal amount of capacity. So now the question is how can we interpret this? So does this look familiar to us? Well, the point is, this thing of course is going to be P, right? So theta times K. So P in general is theta times Q to the minus gamma, right? That was the demand equation. So this is going to tell us, well, if we invest this K star in capacity, well then that's the amount of quantity Q that we're going to produce. So our P star, the price that will be in place for all the rest of time essentially, is going to be theta times is this thing basically, so that's going to be R times I over 1 minus gamma. In order to interpret this, what we can actually do is, in order to make this resemble something that we might know for microeconomics in particular, is have a look at what's P star minus the per unit per time investment cost, or the capital cost essentially of this investment I. So RI, if you agree, is the per unit time investment cost. So if you invest I, so this is the cost, the marginal cost of investment, so that's the cost of capital R. So what is that? That's going to be RI divided by 1 minus gamma minus RI, and that is of course Ri divided by 1 minus gamma minus, let me just do the fractional computation here, and this is of course going to be gamma times Ri divided by 1 minus gamma. So we know that, in other words, just repeat this, P star minus Ri is gamma divided by 1 minus gamma times Ri, or in other words, since we know that Ri divided by 1 minus gamma is P, it's the same as gamma times P star. So what this tells us is that P star minus Ri divided by P star equals gamma. So question, does this look familiar? Do we recognize this kind of expression, preferably from something in microeconomics? So what I'm claiming here is, well, this is price, obviously. P star is the price that we get in for this monopolist when it invests in the optimal amount of capacity, K star. Ri, as I mentioned, is the cost, and the marginal cost rather, of producing this capacity, of building this capacity, K. And what this therefore says is this expression up here, that's the price cost margin. So up here we have the price cost margin. We divide this by the price itself. So this is the markup, so price cost margin, that's the markup divided by cost, is going to be equal to gamma. Now I told you actually this gamma has an interpretation. So if we have this demand function P equals theta times Q to the power minus gamma, I told you this is constant elasticity demand, where gamma actually is the inverse elasticity. So what we see here is actually that this price cost margin relative to the price is equal to the inverse elasticity. Now that should ring a bell if you did any macroeconomics course before. So this is just the relative price cost margin, sometimes also called the Lerner index. So what this says is the Lerner index, or the relative price cost margin for this firm in the static benchmark, is just going to be equal to the inverse of 1 over the elasticity. Gamma is the inverse elasticity. That actually is a solution that we can recognize if we have done any microeconomics, any analysis of monopoly in past courses. So that's our benchmark basically. So let me review that on the slides again. So again we have this, so what did we optimize? Well, the total profit flow over time, well, in the end is going to be a perpetuity of profits. minus the total cost of investment, which is the marginal cost of investment, I, times the total amount of total capacity that we invest in, K. That's your total long-run profits. If you maximize that over, how much capacity are we going to invest in? We figured out, oh, apparently this is what the optimal amount of capacity amount to, but this object here essentially is also the price. This is exactly the price that we're going to realize it at each point in time. So this tells us actually the price itself is equal to the per unit cost, capital cost times the total marginal investment cost, divided by 1 minus gamma. And rewriting this a bit, we can write this as the price minus cost, or the price cost margin, is equal to gamma times the price itself. So since gamma indeed is the inverse of the elasticity of demand, this makes sense. This is what we should know. We should know that a monopolist will always make sure that its price cost margin is proportional to price and also proportional to the inverse of the elasticity. That's what monopoly pricing is. So indeed, this model gives us, in the static benchmark case, just gives us standard monopoly pricing, at least in the long run. So to take into account the long run costs, R times I, of long run per unit costs of investment. So what we need to do, of course, is go from here, now essentially do the real option analysis, and we can compare to the static benchmark where actually theta is fixed, and analyze what happens in the real option case where theta is actually going to evolve according to geometric gradient motion. So that's going to be the next thing, and of course what we need to do in order to solve that is again solve some sort of Bellman equation. So we're going to figure out how to invest in capacity, how to invest in K as theta is growing over time. So obviously we're going to expand capacity over time, K is going to grow over time, but how exactly? Well, that's determined by the solution to the real options Bellman equation.